updating my mentors, friends, what I've been doing. So this time I will talk to you about self-interacting dark matter. But before I do that, I will try to answer the question, can we solve the small-scale puzzles all within lambda CDM? I feel that if I don't ask this question, I will lose an audience. Like Avishai just don't believe in alternative models. So I'll address this first very briefly. So what do I mean by small-scale puzzles? I mean the structural diversity of massive dwarfs. Okay? Velocity scale of 80 kilometers per second. They have cusps and cores, used to known as the cusp core issue, but now people regard more on this structural diversity side. Missing satellites and too big to fail. Too big to fail is in some sense also a diversity problem, but it's a diversity problem for satellites. In the sense that we have the Magellanic Clouds up there in Vmax, and the rest of the Milky Way dwarf population have lower Vmax. So there's a gap for the Milky Way. There is no gap for Andromeda or other galaxies, but it's still the satellite velocity structure distribution is broader than what simulations predicts. By structural diversity or small-scale puzzles, I also mean there exists special or extreme dwarf galaxies. I no longer call them extreme. I don't think they're extreme. They're so common in the universe, like UDGs, compact dwarfs. They're so common in the universe. They're not the special extreme. But they're there. We need to reproduce them. We also have dwarf galaxies with mass-segregated globular clusters or star clusters, in the sense that the denser ones or the more massive ones are closer to the center, and the smaller ones are more extended. The extreme version of this might be low-surface brightness galaxies with a nuclear star cluster right in the middle. That's more massive than globular, 10 to the 7 solar mass in the center. We also have DMDGs repeatedly addressed today. It's actually super easy to produce puffy galaxies or core dark matter halos in lambda CDM simulations. Perhaps too easy to produce them. So here we have like a parameterization of the burstiness of star formation on the y-axis, and galaxy compactness or size divided by virial radius of the halo on the horizontal axis. You see a nice correlation. It just reflects the feedback-driven outflow and the cusp core transformation that Zhao Zhou talked about earlier. So all the UDGs up there populate core dark matter halos. We have a problem in the sense that in the size mass plane, okay, the grayscale is the spark survey sample. And all the simulations are just up there. There are too many ultra-diffuse populations, whereas there's no compact dwarf in the same mass range. The same problem can be regarded in this cusp core versus mass plane. So the brighter symbols are the Fire2 simulations, and the fainter transparent symbols are just a compilation of observational samples. You see that at 10 to the 9 solar masses, we are missing cuspy halos. So it's the new diversity problem, not the old cusp core issue that we are talking about. So CDM halos respond to baryonic processes in two ways: adiabatic contraction and feedback-driven gas outflows, which causes expansion and cusp core transformation. So the two effects compete against each other. So they dominate different mass regimes, as Zhao Zhou talked about already. What's interesting is that dense environments amplify this dark matter halo response to baryon processes. What's shown here are what I call the tidal evolutionary tracks, which are just satellite structural parameter as a function of mass loss. So the vertical axis, the subhalo Vmax, normalized to the initial value at virial crossing. Horizontal axis is mass loss. They're called tracks because they do not care about the details of the orbit. They just care about the initial structure of the subhalo at inflow and the fractional mass loss. So if you are more cuspy, you are more resistant to tidal field. Very intuitive. Similarly, for your inhabitant satellite galaxy, if you are initially cored, you puff up. If you are initially cuspy, you compactify. Very, very simple. This helps with enhancing the diversity, but the problem, I think, is that it's not enough yet. So we can use a semi-analytic model, a SatGen in this case that I wrote, to propagate the halo response patterns that we learned from isolated zoom-in simulations. Okay? There are two messages here. First is that simulations disagree among themselves. If you have bursty star formation feedback, you produce cores in the bright dwarf regime. Otherwise, you don't. But we can choose either case, right? We can make the SatGen model to emulate the bursty star formation and then propagate the halo response from centrals to satellites. And that's what we have on the right-hand side. So if we follow the bursty star formation, we have a lot of ultra-diffuse satellites, and we have almost zero compact dwarfs. If it's the other way, right, if the milder star formation, milder star formation, smoother feedback, then you have a little bit of ultra-diffuse and a little bit of compact. I think, although I haven't done like a detailed quantitative study, I think this is not reproducing the full range of structural diversity in satellites yet. The reason why I say that is because of these plots, right? People have been arguing that the disk of the Milky Way helped to broaden this structural diversity by making the rotation curves more diverse. So here are the Andromeda satellites. And see, indeed, in this controlled experiment with and without disk, right, you get more rotation curves go across this lower right corner diffuse satellites. But you may argue that it's not sufficient. You can ask more detailed questions. If we can reproduce Draco and Fornax, which are respectively the compact representative and the diffuse representative of the Milky Way satellite population. So this is a nice work by Dylan Folsom at Princeton, student working with me and Mariangela Licenti. So the question he's after is, we can run thousands of SatGen realizations of Milky Way, okay? And we can see where the Draco and the Fornax analogs are in the observational space of central density. So rho 150 is the density at 150 parsec versus pericenter. And there are other dimensions in these plots that are not shown: stellar mass, info time, etc. So where are the SatGen analogs of Draco and the Fornax? We see that the SatGen can reproduce Draco very nicely within the observational bounds. But for Fornax, which is arguably the most diffuse satellite of the Milky Way, it struggles. Only 0.1% of Milky Way realizations have a real Fornax analog. And its position is off from the observational constraints of central density and pericenter. What about nucleated dwarfs? Initially, we were focusing on this dwarf galaxy. Actually, it's a UDG with like a radially segregated globulars. So we thought it's interesting in the sense that if you think the radial segregation of globular cluster is driven by dynamical friction, then you can use this signal to constrain the halo mass using pure imaging information. That's what we did. So we developed a simple model of GC evolution plus dynamical friction, and my student Jiang just constrain this halo, reproduce the segregation here, and we can also reproduce very nicely the globular mass function. Turns out it's a dark matter poor, not necessarily dark matter deficient, but dark matter poor galaxy with low concentration. In this regard, it's consistent with the standard UDG formation picture of core formation, etc. But my emphasis here is that, right, if you want to form a nuclear star cluster, which is arguably absent here but exists in many other UDGs, right? If you want to form a massive nuclear star cluster, you need Caspi halo. Otherwise, dynamical friction won't work because of the so-called core stalling effect. So this is problematic because UDGs need to populate core dark matter halos. And finally, for DMDGs, dark matter deficient dwarfs, we think that we can use that differential stripping of dark matter and the stars that we see in several simulations, including Firebox. The caveat here is there's numerical disruption of dark matter subhalos. See also the talk just now, right? Which can form DMDGs in another way. So I think, back to this question, can we solve small-scale puzzles within lambda CDM? I think sort of, but none of the solutions is super clean or very satisfactory to me. That's why I picked up this new hobby, SIDM, during COVID. I think it's a very clean, very neat way of solving almost all the small-scale puzzles and giving some like side benefits, which, if I have time, I will mention at the end. It's not a bizarre theory, actually. So if you ask particle physicists like Oren Sloan at NYU and Princeton, he will tell you that ICIDM and the CDM are just the two extreme cases of the same self-interaction, obeying Yukawa-like interaction. It's just that the CDM have a small coupling factor alpha and a very large mediator mass m phi, whereas ICIDM have large coupling factor alpha and a small m phi, so they can efficiently self-interact. And according to particle physicists, the cross-section is described by two parameters, the rest frame cross-section and the transition velocity scale. So beyond this transition scale, say for galaxy groups and clusters, the cross-section is very small. We can ignore that. Usually in simulations and models, we consider constant effective cross-sections because we usually talk about a given halo mass scale. It's not a bizarre theory also in the sense that on the large scales, it must reduce to CDM like predictions. Right? It only modifies the halo center. And it modifies the halo center in a very simple way. It thermalizes the halo center because of the self-interaction. So we start from this bump. This is an NFW CDM-like velocity dispersion profile. So it's hotter in the intermediate regime. So the heat flows inwards and thermalize the central part. When you have a hotter isothermal core, okay, you radiate energy away, you transport energy, heat to the outskirts. And since self-gravitating systems have negative heat capacity, you lose heat and you become hotter. So it's a runaway process. So core collapse catastrophe. So you have, if you look at the central density, it expands, it decreases initially during this isothermal core building stage. And after the core established, it starts to core collapse. So density decrease and increase again. So this naturally gives you diversity, right? There are two methods, two analytical methods that can describe this ICIDM halos. I don't want you to dive into the equations. I will just mention the basic idea. The first one is isothermal Jiang's model. It's very simple. It's just based on the simple idea that the inner halo is isothermal and the outer halo reduces to CDM. Okay? So you can work out the transitioning regime, the radius R1. Essentially, within R1, your scattering is so efficient that you at least have one scattering of dark matter particles within the edge of the halo. So you can equate the scattering rate, density, velocity dispersion, cross-section, equal to 1 over the edge of the halo. You can solve for R1. You just use the CDM halo profile. Okay. And then you can solve iteratively the Jiang's-Poisson equation for the isothermal core until the isothermal core, okay, stitches smoothly to the outskirt of NFW-like outskirt. So in this way, you can, within a second, you can solve for the ICIDM profile. The more complicated or more physical method is this gravothermal fluid model. You can treat the whole halo as a gravothermal fluid. And you solve for this set of partial differential equations that people introduced to describe globular clusters. If you think about it, globulars are exactly like ICIDM halos. They have self-interaction of stars, just a smaller cross-section and unequal mass. So forget about the details of the equation, but at the end of the day, solving this PDE set, you arrive at the density profile evolution as a function of time, and also luminosity profile evolution, mass profile evolution, etc. The two models have one thing in common. They both have 4 parameters: cross-section, age of the halo, and the NFW mass and concentration. The difference is that the isothermal model uses the CDM halo as a boundary condition at R1, whereas the fluid model uses NFW halo as the initial condition. And it turns on self-interaction. Basically, if you have a target halo at ratio 0, it turns on self-interaction in the future. Forget about self-interaction in the past. That causes some problem, as I will show you. You may wonder, how do we capture the so-called gravothermal core collapse that I showed you briefly using this simplistic isothermal model? If you think about it, it won't work. When core collapse happens, the region within R1 will no longer be completely isothermal, right? Because there's a steep temperature gradient building up. But we can capture at least the onset of gravothermal core collapse, at least phenomenologically or effectively. That's how we do it. So I actually found there are 2 solutions, 2 isothermal solutions. The high-density solution usually discarded because they are very far away from realistic halos. A low-density solution that is preferred because they are closer to CDM halos. Okay. And if you increase the cross-section, or if you increase the age of the halo, the two solutions will merge. Okay, will get closer and closer to each other until they merge. And beyond that merging point, you can no longer find the isothermal solution. That marks the onset of gravithermal core collapse. That's how we approach gravithermal core collapse using the simple isothermal Jeans model. All right, we can compare these two methods. The brown and orange lines represent the low-density and high-density isothermal Jeans model solutions. And the black line is the gravithermal fluid solution. And we compare them to cosmological ICIDM simulations and the idealized ICIDM simulations, respectively. It's quite interesting that this very simplistic low-density isothermal Jeans solution agrees with these gray dots, which are cosmological simulations. If you think about it, it's not surprising because the NFW profile, which we use as a boundary condition, contains cosmological assembly history information. The profile shape reflects assembly history. That's why it agrees with the simulation, cosmological simulation better. But the fluid model, by construction, agrees with the idealized simulation, which also uses NFW as an initial condition. But in the literature, both methods are intensively used. So this is the first time that we do this very detailed comparison. So Shengqi Yang, a postdoc at Carnegie, and I did this very detailed comparison and showed that basically the key difference is that the isothermal solution gives you a lower maximal core density and the later maximal core epoch. What about baryons? ICIDM also react to baryons. It's very simple to consider because we can just add a baryonic component rho B into the Jeans Poisson equation. We improve upon the model here by considering also adiabatic contraction. So we first adiabatically contract the CDM halo given the baryonic distribution, and then we evaluate R1 using the contracted halo, and the other steps remain the same. Voila, out of the box, without any fine-tuning. Okay? The models agree with the Fire 2 SIDM simulations beautifully. Two cross-sections. And it only takes 0.1 second on my laptop and takes, I don't know, maybe weeks on the supercomputer, without any tuning. Okay? But the key takeaway here is not the speed, but the fact that the Fire simulation contains star formation and feedback, but our model doesn't. So the fact that they agree with each other implies that gravithermal processes dominate, and the feedback is not important in SID. Let me skip. Let me show you this key plot I want to show. Okay, ICIDM halo response is dramatic. If you just keep the halo, the galaxy mass, the inhabitant galaxy mass fixed, you just increase their compactness. You make the galaxy smaller. You get drastically different behavior. The dashed lines are CDM, contracted CDM halos, and solid lines are SIDM halos. So by varying galaxy size, you can make SIDM halo chord, cuspy, S-cuspy, or even cuspier than CDM. This is still in the isothermal stage, not in the core collapse stage yet. Okay? So it's not necessarily a solution to the structural diversity issue, but it links closely the two aspects, the size of the galaxy and the slope of the halo. What about nucleated dwarfs? Okay. We still need to investigate more closely using simulations and particle tagging, but this cartoon shows you the idea. Initially, you have an NFW host and a normal dwarf, and then as you establish an isothermal core, at the maximal core stage, you have a UDG. Okay. And as core collapse happens, the stars in the middle follows the core collapse to form a nucleus. What about SIDM satellites? Okay. People realize tidal truncation steepens the temperature gradient, steepens the velocity dispersion gradient, so that it facilitates core collapse. But on the other hand, you also have dark ram pressure from the host to the satellites. So this suppresses core collapse. These two effects compete against each other to render diversity. Okay, this is diversity, right? Depending on your ram pressure stripping rate, okay, you can be core collapsed you can core collapse and then suppress to be dark matter deficient, you can directly become dark matter deficient. Okay? And this is like a parameter space spanned by evaporation, dark RAM pressure evaporation rate versus tidal truncation radius. You got basically 2 or 3 regimes. The lower left is the faster core collapse due to tidal truncation. The upper right is the basically you are in the never core collapse regime because of the strong RAM pressure stripping. And where you are depends on your orbit. If you are on a deep low-speed orbit, you are here. If you are on a deep fast orbit, you are up there. This gives you diversity. And indeed, as simulations show, SIDM is flexible enough that it can produce sufficient structural diversity in satellites. So this is the familiar QP2 fail space. Core collapse, the subhalos up there, and the isothermal core subhalos in the lower right corner. So we can also use observations of like Draco central density to put constraint on the cross section. So I will skip the details for the sake of time, but just to mention that the only favored place, the only interesting regime for SIDM is large cross section, the lower right corner. This blue band, where you have the intermediate cross section, gives you like overcoring in this isothermal coring stage. The upper right corner, you are well into the short mean free path or the core collapse regime. So the density would be too high. So to summarize, I think CDM can solve many of the puzzles unsatisfactorily by nurture. Right? There's issues here and there. But SIDM by nature, there's no need for feedback, can solve them all. Thank you. Thank you for your attention.
You kind of touched about it in the end. Ombre, you know me. You kind of touched it in the end. I was wondering if the RAM pressure stripping, because of interaction, also induces more drag, and how does it compare to dynamical friction, and can it lead to, for the satellites to spend more time at the pericenter to get more stripped, and is this an important effect?
Very good question. So we look into this. So the question is, RAM pressure, in addition to stripping the subhalo, also slows down the subhalo. How does it compare to dynamical friction? We find that it's much weaker than dynamical friction, unless you dial your cross-section up to like 1,000 centimeters square per gram. So it's negligible. But there are other aspects affecting the satellite's spatial distribution. Like the host halo will be cored and have a bump at the intermediate regime. So in this sense, if the satellites are tracers of the underlying potential, it can affect the radial distribution of satellites as well. What I didn't mention is the satellite spatial distribution problems, which SIDM can also address. Yeah.
Hi. I'm Gustav. So with a more flexibility in the model, is there a definite smoking gun signal that you can think of, which, even if the observation is not available now, but something that can definitely distinguish it from baryonic effects?
The rotation curve.
So that can definitely distinguish this from CDM plus baryons?
That's a very good question. I think I need to think about it more quietly and carefully. But what I can immediately react is just the nucleated dwarf is like a smoking gun of core collapse. That's difficult to achieve using feedback. So like nucleated ultra diffuse, right? So ultra diffuse needs like feedback for formation in CDM. But the formation of a nuclear star cluster needs mergers of globulars, which requires a cusp. So if you can, have kinematics data that proves that these systems are either cored or cuspy, right? So it's in some sense falsifies CDM. I don't know if it's too strong argument. What do you think about it? Yeah.
Hi, Phil Mansfield. Could you explain the argument for numerical effects being the possible cause of differential stripping in dark matter deficient galaxies?
Yeah.
It's unintuitive to me because I'd expect that in your hydro simulations, the numerical relaxation time of your star particles is going to be shorter than your dark matter particles. So if you're in a regime where that's a big effect, I would expect that the stars would be really heavily impacted by that.
So, like stars have smaller force softening lengths, and dark matter particles have bigger softening. So the resolution is coarser for dark matter subhalo, right? As like maybe in the past few events of Santa Cruz workshop, Frank Vandenbosch showed very compellingly that you really need like a million particle in your subhalo in order to be free from numerical disruption. I think I'm just reiterating that aspect.
Okay, one last very quick question while the next speaker gets set up.
A question from Fangzhou. I would like to ask how the stripping can help to the core collapse.
Oh.
And will the core collapse contract the galaxy size? Would we expect some observable signal there?
So I didn't show it very clearly, but it's just when you strip. Okay, when you strip your velocity dispersion profile on the outskirts becomes steeper than in an isolated case. So the heat flow rate from the isothermal core to the outskirts becomes higher. That speeds up core collapse. Yeah. I haven't thought about whether there can be a clear observational signal of that. Yeah.
So let's continue this discussion at lunch.